Hello, class, and welcome to another math lesson. In fact, this is going to be the last lesson of Module 1. We're on Module 1, Lesson 13, which means it's the last lesson. You have a test coming up. We're going to, next day of class, we're going to review, and then the day after that, you have the Module 1 end assessment. Module 13, though, we have to finish before that. Lesson 13, we have to finish before that. Lesson 13 is comparing with scientific notation. Making comparisons. Greater than, less than, equal to, all that fun stuff. So for today's lesson, you'll need page 123 through 131 of your math book. So get those pages out ready to go. Also get out a page for notes so that you can follow along and write what I write and do what I do and learn what I know. So what are we going to do today? Well, let's start with what we know already. We know how to write in scientific notation. I'm just going to put sci note. You know what that means. We know how to write numbers in scientific notation. We also know how to add, subtract, multiply, and divide in scientific notation. Now, let's talk about comparing. And when I'm talking about comparing, I am talking about greater than, less than, or equal to. All this kind of fun stuff. So let's look at this with an example. Just one example. Let's talk about space. The final frontier. Unless you believe the final frontier is the ocean. The M82 galaxy, which is a galaxy with not a very creative name, is 1.15 times 10 to the 7th light years from Earth. Pretty far. The Leo 1 dwarf, Leo Roman numeral 1 dwarf, probably should have looked it up. I'm guessing it's a dwarf star, but not sure. The Leo 1 dwarf is 8.2 times 10 to the 5th light years away from Earth, which is also pretty far. But the question is, which one is closer? Like if you want to take a trip to one, which one should you aim for first so you don't have to, go back? Like if you're going to visit both of them, you don't want to go to the farthest one first. You want to go to the closest one first, then you want to go to the farthest one. Just makes sense. So let's write down what we know. Let's just write down our facts because we need to compare these and see which one is closer. In other words, which of these is smaller? Well, let's summarize. The M82 galaxy is 1.15 times 10 to the 7th light years away. The Leo 1 dwarf is 8.2 times 10 to the 5th light years away. Which one do you think is closer to Earth? Which one is the smaller number? Take a minute to think about it, make a choice, look at one, pick your favorite. Okay, now hopefully you picked one. Let's talk about, we're going to start with what is the wrong way. Because I'm going to tell you what some people who look at these think. Here's the wrong way to think. Are you listening? Some people look at these two numbers and say, well, 1.15 is less than 8.2. So, because 1.15 lines up with M82, M82 is closer because 1.15. If you're going to walk, you want to walk 1.15. You don't want to walk 8.2. So this is closer than this because 1.15 is smaller than 8.2. And I have one thing to say to people like that. They are wrong, 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 wrong. Wrong, 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 wrong. Wrong, 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 wrong. They are correct. This is smaller, but these numbers are not these numbers because they forgot to look at the place value. You know, a 10 with an exponent is the place value. So they looked at the decimals, they forgot the place value. This idea ignores place value. Place value is important when you're comparing. People who say this is like saying that 8 pennies is more than $1. You ever want to trick a small child and steal their money? You go up to somebody who's young, maybe younger than 5, and you say, "I have 8 pennies. Will you give me your $1 for my 8 pennies?" And most of the time, the kids will trade because they think 8 is more than 1. They don't look at the little kids don't look at place value. You could give them 8 pennies and they'll give you $1. They'll give you a quarter. They might give you a $5 bill because they think 8 coins is more than 1 piece of paper money. They're ignoring the value of the coin and the value of the money. People who look and say 1.15 is less than 8.2 are looking at just a piece of the information. They're ignoring the place value. Don't do this. This is wrong. That's why it says wrong right here. It's wrong. But now let's look at the right way. There's actually 2 ways you could do this correct. Let's look at 2 different strategies. Right way number 1 is to just check the place value. Look at everything. When you do it this way, you see that the M82 Galaxy is 1.15 times 10 to the 7th. That's the place value. And the Leo 1 Dwarf is 8.2 times 10 to the 5th. Look at the place value. Look at the exponents. Because if you do this, you find out that this scientific notation turns into this number. And the 8.2 turns into this number. When you look at the place values, you see the real difference between these 2 numbers. This has 7 digits plus that 1. This is an 8-digit number. This is 5 plus that 1 in front of the decimal. This is a 6-digit number. I don't know about you, but if people are offering me money, do I want 11 million or do I want 800,000? I'm picking the 11 million, not the 800,000. So when you see the number in standard notation, when you look at the place value, you see that the Leo 1 Dwarf is closer to Earth. Always remember, a greater exponent means a greater number. The opposite is also true. A less exponent is a lesser number. So that's right way number 1, by paying attention to the place values. There is another way you could do this. There is right way number 2, where you make the place values match. You match the place value. And we have done this before when doing operations with scientific notation. If you remember, when we have added and subtracted scientific notation, we have needed to make the place values match. So that's how you can also use that strategy to compare. Let me show you. The M82 again is 1.15 times 10 to the 7th. The Leo 1 is 8.2 times 10 to the 5th. I can change this place value to match this. Remember, we've done this before. I can make these both 10 to the 5th. The way I do that is by turning 10 to the 7th into 10 to the 2nd times 10 to the 5th. This, the Leo 1, can just stay the same because it's already 10 to the 5th. And so you've seen me do this before, where the 2 means this place value gets 2 bigger. So we get 115 times 10 to the 5th after I pull out the 2 and combine. So I pull 10 to the 2 out of this one and combine it with this. It moves here, then it moves here, and we get that. And then I get 8.2 times 10 to the 5th. And now you can just look. The place values match. Now you can look at the decimals. And when you look at the decimals, we have 115 and 8.2. 115 is bigger than 8.2, so this is more evidence that the Leo 1 dwarf is closer than the M82 galaxy. It is a smaller number when the place values match. It is a smaller place value. That's two ways to look at it. You can look at the place values and see how they're different, or you can make the place values match and see how the decimals are different. So, two choices to summarize. Look at the place values and see how they are different, or make the place values match and then look at the decimals. You do not do the wrong way and ignore the place values. You have to think about place values. If you don't want to think about place values, I have 2 nickels for your $20 bill. If you only have one $20 bill, I have 2 nickels. It's a good trade. Moving on to some practice. Let's look at exercise 1 on page 123. Exercise 1 says the Fornax dwarf galaxy is 4.6 times 10 to the 5th light years away from Earth, while Andromeda is 2.430 times 10 to the 6th light years away from Earth. Which one is closer to Earth? So which one is closer? I'm going to do it both ways for you. The first way, right way number 1, let's look at the place values. Fornax is 10 to the 5th. Andromeda is 10 to the 6th. Which one's closer? Which one is the smaller distance? Well, which one is a smaller place value? Well, 5 is less than 6. So Fornax is closer because it has a smaller place value. That's it. This is a smaller number because it's a smaller place value. Even though the 4.6 looks bigger, that's just what it looks like. But you remember, you have to think about place values. Do not just look at the surface. Look at the place values too. There's also right way number 2, if you want me to prove it, where I'm going to take Andromeda and show you it's bigger. Because I'm going to take the Andromeda 2.430 times 10 to the 6th, and I'm going to turn it into something times 10 to the 5th so that I can compare it so that the place values will match. This will turn into 2.43 times 10 to the 1st times 10 to the 5th because 10 to the 6th I can split up. After I split it up, you see that this, I need to move the decimal multiplied by 10, which means I'm moving it one place value, and I'm making it bigger, so the 2 gets bigger and turns into a 24.3. times 10 to the 5th. I combined these two. So now when I do that work, Andromeda, which started out like this, is also this distance. Now the place values match, and you can see 24 is bigger than 4, so Fornax is closer. When you compare, use your place value. Okay, let's move on to, you know what, why don't you pause the video, you try exercise 2, talking about 2 subatomic particles. I think, yes, 2 subatomic particles, and seeing which one has the longer lifetime. So you are comparing the tau lepton and the neutral pion. Which one lives longer? Which one is the greater lifetime? Okay, so hopefully you tried, and one of the 2 strategies, maybe you had enough time and you wanted to try both. I'm going to do both for you right now so you can check. Right way number 1, the tau particle is 2.906 times 10 to the negative 13th, and the pion is 8.4 times 10 to the negative 17th. Which one is bigger? Well, we need to look again, and remember, look at your place values. We have negative 13 and we have negative 17. Remember, bigger exponent means bigger number. Well, which number is bigger? Some people might say, well, 17 is bigger than 13. But this is not 17. This is negative 17. Negative 13 is bigger than negative 17. Negative 13 is bigger. It's, remember, greater than just means closer to 0. So negative 13, this is negative numbers. If you need to prove it, draw a number line and see where negative 13 and negative 17 are. Negative 13 is greater than negative 17, so that means the tau with the negative 13 has the greater place value. So tau has the longer life. Let's check our work with right way number 2. Let's write these again. The tau is 2.906 times 10 to the negative 13th. The pion is 8.4 times 10 to the negative 17th. Now, the right way to do this, remember, for method 2 is to make the place values match. So I'm going to change the pion because the pion has a negative 13 inside of it. Watch what I do here. 8.4 times 10 to the negative 17th equals 8.4 times 10 to the negative 4th times 10 to the negative 13th. Negative 4 and negative 13 together make negative 17. Why did I pick these numbers? I picked them so that the 13 here matches the tau. I want the 13s to match. But I still need to get this negative 10 to the negative 4 and combine it with this. Now this is 10 to the negative 4, which means it is moving 4 place values. So this decimal is moving 4 place values. And it's negative, so it's making the number smaller. So it's jumping 4 places this way. So this will turn into 0.00084 after I move it over. But now I only have the 10 to the negative 13th. Now the place values match. Now I can compare. So when the place values match, the tau is 2.906 and the pion is 0.00084. This is the place values match, so I can just look at the decimals now And which decimal is bigger? Obviously, that one's bigger. So, when the place values match, when the place values match, the tau is greater. So whichever way you do it, right way 1 or right way 2, you find out that tau has longer life. You get the same answer for both. Remember, when you're comparing, place value is super important. Let's go to the next page. You get some more practice with this. Exploratory challenge 1, exercise 3. Not going to do it. On page 124, cross that thing off. Skip straight to exercise 4. Compare these two numbers. Well, let's check. Remember, we're comparing. First thing we should always do is make sure the place values match. Look at the place value. Look at the place value. Guess what? The place values match this time. So when the place values match, just go straight to look at the decimals. So let's look at the decimals. We have 9.3 and 9.2879. Now, some people will say, and it's okay, but it's time to fix this misconception. This is bigger because there's more numbers. Is it really, though? Because can't I just add zeros here behind the decimal? Now they have the same number of digits. 5 digits, 5 digits. Did I change anything? No, I just put zeros. Zeros don't change anything. Not when they're behind the decimal like this. They don't change anything. But it makes it clear which one's bigger because you're like, wait, which one's bigger now? Is 3,000 bigger or is 2,897 bigger? We don't even look at all of these. Those don't matter. What matters is right here. The 3 is greater than the 2. So a 9.3 is great even if there's a lot of numbers. I can keep writing numbers for infinity here. This number will always be bigger because it has 3/10 instead of 2/10. The 3 always beats the 2, so it doesn't matter what comes after. So if you're writing the comparison here, you need to write that 9.3 times 10 to the 28th is greater than 9.2879 times 10 to the 28th. Hopefully you get that. It's about comparison. Stuff you've been doing for years, except for now we've got scientific notation. Let's look at exercise 5 because Chris made the same mistake some people might have made with exercise 4. Chris said that 5.3 times 10 to the 41st is less than 5.301 times 10 to the 41st because 5.3 has fewer digits. So he said, this has 2 digits, this has 4 digits, so this one is smaller. That's what he said. 2 digits, 4 digits, this one is smaller. Now, Chris's answer is correct. It is less than. But it's for a different reason than he said. He has the right answer for a completely wrong reason. He has the right answer, but he still doesn't know what he's talking about. His reasoning is flawed because he's making the same mistake people make. He's not looking at the place values. The place values are the same. And if the place values are the same, they have the same number of digits. You cannot say this one has 2 digits and this one has 4, because after a decimal, you can keep adding place values. So like he saw 5.3 and he saw 5.301, and he said, here, I'll even put on the place values. He saw this and he saw this and said, oh, well, this has more, so this is bigger. What I would tell Chris is what I would simply go up to Chris and say, what if I put zeros there? The number didn't change. The zeros didn't change anything because they're behind the decimal. Now they both have 4. So Chris, is the number of digits why this one is greater? No. This one is greater because the 1 is greater than a 0. This one is greater because 1 is greater than 0. It has nothing to do with the digits. Digits do not matter here because the place value is the same. They have the same digits. I can keep adding zeros for as long as I want. It's the value that's important. The digits don't matter. It's the value of those digits. So if you ever meet Chris, slap him in the face for me. Okay. Next page, 125. Not going to do it. Next page, 126. Not going to do it. Next page, 127, the exit ticket. We are going to do it. Almost had you there, didn't I? Number 1, compare those two numbers. Which one is larger? You can use method A, where you look at the place values, or you can use method B, where you make not A and B, right way number 1, or where you look at the place values, or you can use right way number 2, where you make the place values match. Try it on your own. Write a comparison sentence. So what I want to see at the bottom of this, 2.01 times 10 to the 15th, and 2.8 times 10 to the 13th. I'll even make it multiple choice for you. It's less than, greater than, or equal to. Pick one of those, put it in the circle, but show me the evidence why. You can check your answers online with the ones I posted and check your answers with mine, and then see if you have the right answer. If you don't have the right answer, figure out why. If you can't figure out why, ask me for some help. For number 2, the wavelength of the color red is about, red is this. That's the wavelength. The wavelength of the color blue is this. And then they want you to show me that the wavelength of red is longer. Can you show me that red is longer? How will you show this to me? What is your evidence? Can you explain why red is longer? This one I'm telling you, red is greater than blue. But I want you to prove it using one or both of the right ways. Prove that red is greater than blue. Once again, check the work online. I have the answers online, so you can check your work. And if you are still confused, you can ask me for some help. The next page, page 129, is the homework helper. Excellent tool to use. It will explain everything again, maybe even better than I did. On page 131, we have the problem set. Now, number 1, we are not going to do. But number 2, we will. Number 2, it says the mass of the neutron. So we have the neutron is 1.674927 times 10 to the negative 27th kilograms. And then it says the mass of the proton is 1.672622 times 10 to the negative 27th kilograms. Which one is heavier? In other words, which weight is greater? How can you do this? How can you know? I really want you to explain how. Once again, check your answers with what I post online, and if you're stuck, ask me for help. But my explanation is online for this one. For number 3, there's 2 parts. The average lifetime of the Z boson is approximately that many seconds, and the average lifetime of the neutral row is that many seconds. Now, I'm okay if you use a theorem from today's lesson. Just somehow explain why the neutral row has a longer average lifetime. So they are telling you that the row is greater than the Z boson. They tell you this. The row is greater than the Z. Explain why. Excuse me. Explain how you know. Use one of the strategies. If I were you, I might look at the exponents, look at the place values. For part B, it says, how much longer is the lifetime of the row than the Z? Now, how much longer is evidence that this is a subtraction problem. So the row is longer, but how much? So this one, you need to do the row minus the Z. Can you do the row minus the Z? In other words, you take the row, which is 4.5 times 10 to the negative 24th, minus the Z, which is 3 times 10 to the negative 25th. Can you solve that using all the skills we've learned? This is good practice for your test coming up in a couple days, because you will probably have to do some subtracting of scientific notation. But once again, the answers are online, so you can check your work and show off. And once again, I am online, so you can ask me for help with whatever you need. Study for the test. Go on Khan Academy. Go on MobyMax. Do some more practice. Read your notes. Check your notes. Check your work against my work. Make sure you are doing the right thing. And I will see you for the next lesson next time.